All right, my friends, we're beginning our lesson on velocity. I have my book open to page 9, section 1.3 of our journey, velocity. We define that in terms of uniform motion of constant speed. The velocity of uniform motion in a motion diagram would be that of an equally spaced motion particle. To kind of emphasize is what we're saying, I'll just kind of show in our book a diagram. Motion diagram for a car and a bicycle. This is figure 1.16. It says during each second the car moves twice as far as the bicycle. The car therefore must be at a greater speed. You can see the distance between each of their particle dots, their motion particles, are indeed uniform, showing constant velocity or uniform motion. Since the car made it a further distance in the same amount of time, we can clearly see that it is traveling at a greater rate. So we're just looking to kind of get our first grip on how we calculate something called speed. Looking at this particular diagram from the book, or here it is in the PowerPoint as well. The book provided a little color, but we can see that we are calculating speed by taking distance traveled in a given time interval. So how far did it go over a certain amount of time? The change in the distance over the change in time. If we were to look at car, which is the top area, moving 40 meters in 1 second, from time 0 to 1 second, the distance that it traveled, the distance is 40 per 1 second. We just report that out in a 40 meters per second. Now the bicycle only made it in 1 second. It only made it 20 meters, which we would report as 20 meters per second. The per is showing a ratio. In every 1 second, it was traveling a certain distance. Bike 1 is moving to the right. We see this kind of arrow here showing its magnitude. Bike 2 is moving to the left. So we're looking at kind of an opposite direction here. So if we think about average velocity, and I'm just kind of giving us this page number as well, we're looking at page number 10, if that's something you'd like to look closer at your book. The two bicycles are traveling at the same speed, but now we're seeing that they have different velocities. So if from time 0 to time 1, bicycle 1 traveled 20 meters, bike 1 has a velocity of 20 meters per second. Bike 2, I needed to read more carefully. Look, these are in feet, not meters. Feet per second. Bike 2, here we are traveling from time 0 and 1 second later. This is a negative direction, but it's simply showing that this particular bike is traveling west. The up above bike here was traveling east, so they're just opposite directions. From 20 to 1, here we're looking at going from 120 to 100 is 20 feet per second. So the average velocity here is just kind of showing us that we're looking at bike 1 moving to the right, bike 2 moving to the left, and we can simply calculate very quickly how the velocity, just displacement over time interval, is showing us a moving object's speed. The difference, of course, between speed and velocity is a vector, and that just means it's telling us what direction the motion is occurring in. So the object's speed must also include the direction to turn it into a velocity. This motion diagram of two bicycles traveling at both the same 20 feet per second, but they're just going in opposite directions, so the direction of their motion is different. Therefore, their velocity is different. That's an important thing to say. Their speed is the same. We can see the speed is the same. To show the difference in the term velocity, bike 1 has a positive direction, bike 2 has a negative direction. One's traveling east of the origin, one's traveling west of the origin, and therefore their velocities are indeed different. They must be traveling the same way for the velocities to actually match. So that's an important note. Speed could be identical, but once we had put on a positive and a negative sign, the velocities do indeed become a different value. Notice that we've used the x2 for the position at time 2 seconds and x3 for a position at time equal 3 seconds and so forth. And those subscripts are just serving the same role as before. They're just identifying the particular positions, but in this case the positions are identified at the time at which each position is reached. Here's an important statement in our text, and it's just, I see that it is highlighted as well, kind of in bold-faced terms. Speed measures only how fast an object moves, but the velocity tells us both an object's speed and its direction. And I could just emphasize that by saying that's indeed what a vector quantity is all about. The direction is included to turn the speed into a velocity. Let's take a peek at an example problem. At time equal 12 seconds, Frank is exactly at x equal 25 meters. 5 seconds later, he's at x equal 20 meters. What is Frank's velocity? Well, we're trying to get in the pattern of model first, math second. So let's begin by creating a coordinate system. And we'll create a point of origin and call that 0. 25 meters could be represented just putting down on the x-axis here 25 units, and it's not important to put a line for each 25 hash ticks, but we could just say right here represents 25 meters, and that's at time equal 12 seconds. 5 seconds later, time has gone by, and he's gone now to point 20 meters. On the x-axis, he's 20 meters. So time 1, or initial, is 12 seconds. Time 2, we can see 5 seconds later, and you can think about 5 seconds later would be 17 seconds. 17 seconds would be 5 seconds later than when we started, and now we're at a distance of 20. The change in distance over the change in time will be used to calculate velocity, and remember, velocity will have a direction. Since he is heading toward the origin, he is heading west, this will need to have a negative magnitude. He's heading back toward the origin. So just thinking through the sign, the change in distance, well, he's traveled from 25 to 20. And a total time that elapsed was the 5 seconds later. 17 minus 12 gave us the 5 seconds. So you can see that he is traveling. Change in distance over change in time, and you can just kind of take a peek if you wanted to just practice your calculator. I know it could also be mental math, no problem there. But 25 minus 20 clearly sees that this is 5. 5 divided by the 5 will give us 1. 1 meter per every second. But now, friends, here's the critical part. It's got to go into a negative magnitude. The direction of the velocity is heading toward the origin, showing us a negative velocity. The negative sign shows it's heading west. -1 meters per second. That's Frank's velocity in our example problem. We'll try another. And this is section example 1.2. And if you're following in your text, it's on the bottom of page 10. It says albatrosses are seabirds that spend most of their lives flying over the ocean looking for food. With a stiff tailwind, an albatross can fly at high speeds. Satellite data on one particularly speedy albatross showed it going 60 miles east of its roost at 3 p.m. Now that's kind of an interesting point. Let's say here's its roost. We'll say that that is the origin. 60 miles east means in the positive direction. I'm going to record. We spotted the bird 60 miles east of its roost at 3 p.m. At 3:20, 86 miles east of its roost, it was spotted again. So here we have time 1, 60 miles east of the roost. Time 2, which is 20 minutes later, 3:20, we spot it at 86 miles east of the roost. What is its velocity? Velocity, we know, the change in distance over the change in time as a vector quantity. We can clearly see that the vector quantity here, from the point of the first sighting to the point of the second sighting, is heading east. It will have a positive value. So just thinking that it's heading on the positive side of the number line, we know that the velocity ends with a positive magnitude. Change in distance can be found by just a simple subtraction, 86 miles and 60 miles. There's the distance. And the change in time from 3 p.m. to 3:20 p.m. is 20 minutes that have gone by. But now, as a scientist reporting out common units, we very rarely hear miles per minute. The more acceptable value is miles per hour, and so we're going to work it out to something that we're commonly familiar with. Miles per minute is an acceptable unit in terms of what I'm seeing here, but we'll just practice that unit conversion as well into a more familiar unit, miles per hour. So let's go ahead, and I know this is mental math, but we'll get in the habit of just showing what I'm doing on the calculator screen as well. And 86 minus 60 gives me the change in distance is 26 miles over 20 minutes. That's what I'd like to do, is to convert that into miles per hour. So this is an opportunity to practice the skill. It's going to come up again later in just unit conversions. We know that 26 miles per 20 minutes. We know that there are 60 minutes in every 1 hour. And all this is going to do for me is cancel the minutes, and now I'm left with miles per hour. So I can clearly just kind of set up a conversion factor, a series of equivalent values that allow us to cancel units, and it's a practice skill that this chapter emphasizes. Our 26 divided by 20, our first ratio, times 60 over 1 gives us a value of 78. So when I'm hitting out, I get 78 miles per hour. I'm looking here, and it's again another topic that will come up. 79 miles per hour is what the text answered, and I just wanted you to know that when they put a fraction in, 20 minutes is indeed a third. 0.33 repeating is a third, but that's a truncated fraction, 0.33. When we set up our conversion factor, it did carry more significant figures, so 78 was the way that ours came out, just by the mere fact that we didn't put in a truncated value for that fraction. So just to kind of share it, we're going to end up with a different sig fig, different significant digit, and that's okay. The process was just the practicing of canceling units. So calculating change in distance over change in time for velocity, and we got to practice some unit conversion with this particular problem. I would turn off the video here, go through the section 3 very carefully, doing some of the homework problems, and when you feel like you've mastered the material, start the section 4 video lesson.